All right, ready for another deep dive.
Always.
Today we're tackling something pretty wild, circadian lighting.
Oh, yeah.
Our listener this time has sent us a mountain of research calculations, even some code. Someone's been busy.
Clearly a lot of passion for this topic.
Absolutely. This listener is serious about getting their indoor lights synced up with their natural rhythms. And, they're taking a DIY approach to this, which I think is super cool. So before we get lost in the weeds, I think a quick overview is in order. We're talking circadian lighting. The source material is heavy on the technical side. And our mission, should we choose to accept it, is to break this down into understandable chunks for everyone.
Sounds like a plan.
Mm.
And it's not just about understanding it. It's about seeing why this is such a fascinating area, why people are putting in this effort to hack their lighting.
Exactly. So before we even touch the tech, can you give us that circadian rhythms 101? What are they and why should we care?
Sure. So circadian rhythm, it's basically your internal clock. It runs on a roughly 24-hour cycle, and it's responsible for a ton of stuff going on in your body.
Like what kind of stuff?
We're talking sleep-wake cycles, obviously, but also hormone release, body temperature, even things like how your cells repair themselves. And light, natural light, is like the conductor of this whole orchestra.
Okay, so that makes sense why messing with our lighting indoors could throw things off.
Exactly. We evolved with this natural light-dark cycle, and now we spend most of our time under artificial light, which can confuse the heck out of our bodies.
Right. Hence, circadian lighting, trying to mimic that natural cycle indoors.
Exactly. And that's where all this research and tech comes in.
Now, one thing that caught my eye right away was the use of what you called sample circadian rhythm data. You're not actually measuring your own rhythms, right?
Right, that's a key point. There just aren't that many readily available sensors that can accurately track how much color temperature a person is exposed to throughout the day, not in a way that's practical and affordable, at least.
Huh. You know what? I hadn't even considered that. We have all this amazing tech, but sometimes even getting the basic data is a hurdle. So how do you work around that lack of personal data?
Well, this project relies on a bit of mathematical modeling. It turns out there's a pretty good correlation between color temperature changes throughout the day and a specific type of curve, a parabola.
Wait, parabolas, like from
Yeah.
high school math class,
Yeah.
flashbacks to graphing equations.
No worries, no pop quizzes here. But yeah, it's a surprisingly good fit for modeling how color temperature shifts throughout the day. And there's some serious science behind this. You mentioned a machine learning paper in your notes.
Right, now you're speaking my language. Machine learning, AI, those are my jam.
Well, in that paper, researchers used algorithms to analyze a bunch of complex circadian rhythm data. And what they found was these parabolic curves popped up as a significant pattern.
Oh, that's fascinating. So they're taking these insights from AI, from this data analysis, and applying them to this lighting system.
Exactly. And what's cool is how the system then takes that parabolic curve and adjusts it based on your location and the sunrise and sunset times for that day. So it's personalized in a way, even without tracking your exact light exposure.
So it's kind of like it knows the general shape of the light curve for your day just based on where you are in the time of year.
Right. And in your notes, you even highlighted how they visually squish the graph to adjust for different day lengths. It's a really nice way to visualize how the system adapts throughout the year.
Yeah, I love that detail. Made it so much easier to picture. Okay, I'm following you so far, but I have a feeling things are about to get a little more, shall we say, math intensive.
You're not wrong. But hey, that's what makes these deep dives so fun, right? We're about to go from parabolas to wavelengths and LEDs.
Bring it on. Hit me with that science.
All right, so let's start with the fundamentals. Light, as we perceive it, is made up of electromagnetic waves, and it's the wavelength of those waves that determines the color we see.
Right, like longer wavelengths are toward the red end of the spectrum, shorter wavelengths are toward the blue end, yeah.
Exactly. And the visible spectrum, all those colors we can see, that's just a tiny, tiny sliver of the entire electromagnetic spectrum.
Right, there's all that stuff beyond red and violet that we can't see, like infrared, ultraviolet. But how does this tie back into circadian lighting?
Well, this is where things get interesting. Our eyes, they've got these special cells called cone cells, and these cells are sensitive to different wavelengths of light. And we've got 3 types of tone cells, each one most sensitive to a specific range of wavelengths.
Okay, so are we talking red, green, and blue wavelengths here?
Mm,
Because I'm sensing a connection to RGB LEDs.
spot on. That's exactly why RGB LEDs are used in this kind of system. They can produce light in those specific red, green, and blue wavelengths to mimic the color of natural light. But to really do that, we need to understand how those wavelengths translate into what we actually see, what we perceive as color.
Okay, now I'm really curious. Lay it on me.
So think of it this way. Each type of cone cell, the red, green, and blue ones, they're sending a signal to your brain based on how much light they're picking up, how much they're being stimulated. And it's the combination of those three signals that creates the color you see.
So it's like our brains are constantly doing this insane amount of processing, taking in all this complex information about wavelengths and boiling it down to just these three signals,
Yeah.
red, green, blue.
Exactly. Our brains are amazing like that. And this project, it taps into that whole process using a concept called the sense vector.
Sense vector.
Yeah, it's a way of representing how our eyes would perceive a specific light source, even a really complex one, using just those three values, red, green, and blue. Basically, it captures the essence of the color in a way that our brains can understand.
Okay, I think I'm getting it. So to match the color of, say, sunset, the system needs to figure out what the target sense vector would be for that particular light.
Exactly. And to do that, it needs to know how much each type of cone cell would be stimulated by the different wavelengths that make up that sunset light. That's where things get a bit tricky.
And that's where this CIE 1931 beta set comes in. You mentioned it in your notes, and it sounded like a pretty big deal.
It's essential, really. It's like a map of human color perception. It contains super precise data on how different wavelengths of light stimulate those three types of cone cells we were talking about.
So the project uses this data set to calculate the right blend of red, green, and blue light from the LEDs to create the desired color temperature.
Precisely.
Okay.
But it's not a direct jump. There are a few steps involved. First, you got to translate the desired color temperature, which is usually measured in Kelvin, into its corresponding coordinates in a special color space called CIE XYZ.
XYZ in another color space. We're going deep down the rabbit hole here. I'm starting to get a little lost.
Don't worry, it sounds more complicated than it is. The main thing to remember is that XYZ is just another way to represent colors mathematically based on how we perceive them. It's like a universal language for color, if you will.
A universal language for color. Okay, that helps.
Good. So once we have the XYZ coordinates for our target color temperature, then we can convert those to the sRGB color space.
Which is what our LEDs actually use, right?
Exactly. sRGB is the standard for digital displays and LEDs, so that's the final step to make sure the colors actually show up correctly.
Okay, got it. Now, in your notes, you briefly mentioned something about integration and a function called numpy.traps. Was that related to this whole color conversion thing?
You're sharp, yes. Integration is used to calculate the total stimulation of each cone cell type across the entire visible spectrum. And numpy.traps is just a handy function from a programming library called NumPy. It's a really efficient way to perform that integration calculation.
So basically, it helps get a more accurate picture of how our eyes would respond to the light.
Exactly. And all of this, the sense vectors, the different color spaces, the integration, it's all working together to make sure those RGB LEDs can accurately mimic natural light.
It's amazing, you know.
Yeah.
You don't even think about all the complexity that goes into something as seemingly simple as changing the color of a light bulb.
I know, right? It's fascinating. And speaking of colors, you mentioned something called color-specific matrices in your notes. What were your thoughts on those?
Oh, those were cool. It's like taking this whole system and giving you even more control. You can actually tweak the lighting to create specific moods or atmospheres in different environments.
I see where you're going with this. And you even pointed out some examples in your notes.
Yeah, like they mentioned using a greenish tint for hospitals, warmer tones for cozy spaces, and even a bluish tint for places where you need to focus and be productive.
Exactly. It's about adding that extra level of customization, going beyond just matching the color temperature of natural light. Those matrices basically let you fine-tune the color output to create a very specific ambiance.
I mean, just thinking about all this, you really start to wonder how much of our mood, our energy, even our health is tied to the lighting around us. You know, we spend so much of our lives indoors.
It's a huge question, and honestly, one that researchers are still trying to fully understand. But there's no doubt that light plays a big role. And that brings us back to those two specific questions you wanted to dig into.
Right. First up, question number 3, all about the different algorithms used in this project. We ready to tackle that one?
Let's do it. It's a good opportunity to recap some of what we've talked about so far.
Okay, so first on the list, we've got Gaussian curve fitting. Now, remind me, what was that all about again?
Yes. Remember those parabolic curves we were talking about? Well, Gaussian curve fitting is the math behind finding the best fit parabola for those color temperature changes throughout the day.
Right, so it's basically smoothing out the data, finding that nice gradual curve that captures how the color temperature shifts from morning to night. But what was the point of using this specific algorithm? Were there problems with the way this was done before?
You know, the source material, it didn't specifically call out any limitations in existing approaches for this part. But the real key here is accuracy, getting that smooth, gradual change that reflects how color temperature shifts throughout the day.
So a Gaussian curve, it just gives a more natural representation of that change compared to something simpler like a straight line.
Exactly. And remember, this isn't just some random curve they came up with. It's based on those patterns they found in the actual circadian rhythm data, thanks to that machine learning research we talked about.
Ah, so it's leveraging those AI insights to build a better model.
Well,
Pretty cool.
hmm.
What about the contribution of this project specifically? Did they do anything unique with Gaussian curve fitting?
Well, what's clever about their implementation is how they combine this technique with the sunrise and sunset data for your location. So instead of using just a generic curve, it personalizes it based on your actual day length and the time of year.
That's a really nice touch. It makes the system way more adaptable to wherever you are in the world. Okay, next algorithm on our list. What's up next?
Next up, we've got the color temperature to XYZ conversion.
Ah, yes, the whole translating from the Kelvin scale to the XYZ color space thing. What were the main challenges they were trying to address with this algorithm?
The main challenge here is just the sheer complexity of the relationship between color temperature and those XYZ coordinates. There's this formula involved called Planck's law, which basically describes how different objects emit light based on their temperature. It's a bit physicsy.
Okay, you lost me at Planck's law.
No worries. The main thing to know is that it's a complicated calculation. But the good news is we don't need to understand all the physics behind it to appreciate what this project has done. They basically found a really smart and efficient way to do this conversion using what's called numerical integration. And again, they're using the NumPy library to handle the heavy lifting.
So they've essentially streamlined this complex calculation and made it work seamlessly within their system.
You got it. And as far as limitations in previous approaches, the biggest challenge is often finding that sweet spot between accuracy and computational efficiency. Some methods might be super precise, but they take a ton of processing power, which just wouldn't work for a real-time system like this.
Makes sense. So it's not just about doing the math, it's about doing it in a way that's practical for the application.
Hmm.
All right, what's the next algorithm we got to break down?
Algorithm number 3, the XYZ to sRGB transformation. Remember, this is where we go from those theoretical XYZ color coordinates to the actual colors our LEDs can produce.
Right, because XYZ is more like a mathematical concept of color, but sRGB is what our screens and lights actually use. What are the potential issues with this conversion?
Well, the standard conversion matrices that are often used can sometimes give you RGB values that are outside the displayable range. It's like trying to turn up the volume past the maximum setting and just can't go any further. And that can lead to what's called clipping, where the colors get cut off, or you just get inaccurate color reproduction.
So basically, colors might look duller or less vibrant than they should be.
Exactly. And that's where this project shines. They've implemented a normalization step that makes sure all those RGB values stay within the valid range. It's a small detail, but it makes a big difference in how accurate those colors look.
Like a safety net for the colors. Okay, last algorithm on the list. Those environment-specific matrices we talked about earlier, those are my personal favorite.
Mine too. They add so much potential for customization. It's like the artistic side of this whole project.
Totally. But was there something specific they were addressing with these matrices? Like, was there a gap in how previous systems handled this kind of fine-tuning of the colors?
You hit the nail on the head. You see, most circadian lighting systems out there, they're really focused on just matching that natural light color temperature. They don't necessarily give you a lot of control over the actual hues or tints.
So these matrices, they give you those extra knobs to tweak?
Right. Exactly. They let you bias those colors towards a specific shade, depending on the mood you're going for. You mentioned green for hospitals, warm for cozy spaces, blue for productivity. Those are all great examples.
It's like having a whole set of filters for your lights. But were there any limitations with previous systems that these matrices help overcome?
Well, some systems do offer basic color temperature adjustments, but they're often pretty limited. They don't give you the same level of granularity and control that these matrices do. This project's approach is much more systematic and precise, and it opens up a lot more creative possibilities for playing with color.
I love how this project combines the science, the hard data on light and color, with this artistic element, this ability to create different experiences with light. Okay, so we've covered those four algorithms in depth. Now, I think it's time for the big question. Why should we even care about circadian lighting? What are the real benefits, and can we even measure those benefits in a meaningful way?
Ugh, the million-dollar question. And to be totally honest, it's a question that researchers are still trying to figure out definitively. But we can definitely use what we know so far to make some educated guesses.
So you're saying we can take a stab at predicting how impactful this kind of lighting could be.
Mm.
All right, I'm game. What kind of improvements are we talking about here?
Well, we have to start with the foundation, right? Circadian rhythms. Those rhythms, they impact so many things in our bodies, and one of the most important is our sleep-wake cycle.
Right, right. When our internal clock is in sync with that natural light-dark cycle, we sleep better, we're more alert during the day, all that good stuff.
Exactly. So the thinking is, if we can align our indoor lighting with those natural rhythms, we should see improvements in sleep quality, less daytime sleepiness, maybe even better cognitive function.
That makes sense intuitively.
Hmm.
But do we have like actual scientific evidence to back that up?
We do. That machine learning paper you sent over, they found that exposure to brighter, bluer light in the morning can actually shift the circadian rhythm earlier. It makes it easier to fall asleep at night and wake up feeling more refreshed.
Oh, interesting. So there's data to support that whole blue light in the morning thing.
Yeah, and on the flip side, dimming the lights and reducing blue light in the evening, that can help signal to your body that it's time to wind down, which could lead to better sleep.
Okay, so better sleep, that's a big one. But you mentioned other potential benefits too, right?
Right. Some studies have shown that exposure to bright light, especially in the morning, can also improve mood, boost alertness, and even reduce those symptoms of seasonal affective disorder, SAD.
Wow, that's pretty amazing. I can see how that would be especially helpful during those dark winter months. It's like bringing a little bit of sunshine indoors.
Yeah, exactly. Now, research is still ongoing, but there are even studies suggesting that circadian lighting could have positive effects on hormone regulation, metabolism, maybe even cognitive performance. There's a lot we're still learning about this.
It's incredible to think about the potential here, but the listener also asked about actually quantifying these benefits.
Hmm.
Can we put like a percentage on how much this kind of lighting could improve sleep or mood?
That's where things get a little tricky. It's hard to give really specific predictions because everyone's different, their circadian rhythms are different, their lifestyles are different. There's just so many factors that come into play.
So it's not a one-size-fits-all kind of thing.
Exactly. And we have to remember, a lot of the research on this is still pretty new. We need more long-term studies to really nail down the specific benefits and how they vary from person to person.
So it's more about exploring the possibilities and seeing how it works for you individually.
Exactly. But based on what we do know, I wouldn't be surprised to see, say, 10 to 20% improvements in sleep quality for some people. And even those small improvements in sleep, they can have a ripple effect on so many other things. Energy levels, mood, how well you think, all of that.
It's just fascinating to think that something as simple as light could have that kind of impact on our well-being.
I agree. It's a really exciting area of research.
Well, you've definitely given me a lot to think about, and I'm sure our listeners are feeling the same way. Big thanks to our listener for sharing this project with us.
Yes, absolutely. This has been a really fun deep dive.
And to everyone listening, if you're at all intrigued by this idea of circadian lighting, do some digging, maybe even experiment a bit yourself. You might be surprised at what you discover.
That's what the deep dive is all about, exploring new ideas, pushing the boundaries of what we know.
So until next time, keep those minds curious and keep exploring.
See you on the next deep dive.